Good morning, class. My name is John Mark Astorga, your chemistry teacher for today, and we will be discussing about chemical equilibrium. But before we proceed to our main topic, I would like to set some objective for today so that at the end of the day, we'll be able to explain that what is meant by chemical equilibrium, write the equilibrium constant expression for any reaction, apply the equilibrium constant to reflect changes in the chemical equation, calculate an equilibrium constant from concentration measurement, and lastly, explain how important Le Chatelier's principle. And for that, to start with our topic for today, let's define equilibrium. Equilibrium comes from the Latin terms equus, means equal, and libra, means balance. Therefore, equilibrium indicates the state of balance in chemical reaction. Chemical equilibrium occurs when opposing reactions proceed at equal rates, that the rate at which the products form from the reactants equals the rate at which the reactant form from the products. As a result, concentrations cease to change, making the reaction appear to be stopped. Like for example, in our household, when we arrived at school when we arrived home after school, we will ask our parents or our mother a snack, and our parents will prepare a fruit juice, for example, and that fruit juice is added with water and added with sugar to results sugar solution. That is an example of a forward reaction. In the meanwhile, after adding too much sugar, we would notice that the sugar solution crystallizes again. That indicates that the saturation point of a solution has been reached. And this is the way how are we going to represent the chemical reaction. Sugar solution to form sugar plus water. On the other hand, we can be able to write this chemical reaction. Water plus sugar will give us reversible reaction. You can see the arrow forward and then the arrow backward. That is a reversible reaction to produce sugar solution. In chemical equilibrium, we also observe some characteristics of a system. First, it is a closed system, meaning there will be no change at all on the matter in the system. For example, water cannot be evaporated in the system in the same manner that water cannot be added in the system, because the system in the equilibrium is closed. Second, there is no visible change in the properties of the system as time passes. As for example, such as the concentration, the color, and then the temperature. The two processes, which are opposite in the direction, simultaneously takes place at the same rate. As going back on the definition of chemical equilibrium, is a state of a reversible reaction where the rate of the forward reaction equals to the rate of the reverse reaction. Furthermore, at this point, there are still reactants present, but there does not appear to be any further change taking place. There's no more reaction because the chemical reaction has completed and reached its equilibrium state. While a reaction is in equilibrium, the concentration of the the reactants and products are constant. There are two types of chemical equilibrium. One, we have the homogeneous equilibrium, which has everything present in the same phase, like for example, solid and solid, liquid and liquid, and gas and gas. So, like we have here, for example, the hydrogen gas and the vapor of iodine. So, iodine, we know that it is violet in color. With the introduction of heat at 763 degrees Celsius, we will be able to have a reversible reaction producing 2 moles of hydrogen iodide in a gaseous state. The second type of chemical equilibrium is a heterogeneous equilibrium. Has things present in more than one phase, be like, for example, solid and gases or solids and liquids in one chemical reaction. For example, in this matter, we have solid and liquid. So bismuth chloride plus water will produce a reversible reaction, bismuth oxyl chloride. Bismuth oxyl chloride which will precipitate plus the 2 moles of hydrochloric acid in a liquid state. So, our product is solid and liquid. Do you have any other questions so far? Great. So now, if you can see here on this chart or diagram that we have on screen, the chemical equilibrium is the state in which both reactants and products are present in concentrations which have no further tendency to change with time. So we are correlating the concentrations versus the time on the product and the reactants. The chemical equilibrium is achieved when the rate of forward reaction is same as the reverse reaction. Since the rates are equal, there are no net changes in the concentrations of the reactants and of the products. This state is known as the dynamic equilibrium. Next, we have the law of chemical equilibrium and equilibrium constant, or K sub C, or in other reference, we use KEQ. Chemical equilibrium can easily be understood by understanding chemical kinetics. It is the study of the rate of the reactions under various conditions. So that includes the temperature, the concentration, and so on. Also, it includes the law of mass action that states that the rate of a chemical reaction is directly proportional to the product of the concentrations of the reactants raised to their respective stoichiometric coefficients. So later on, we will be seeing what is the stoichiometric coefficients means. So on our given reaction, as represented by A, B, C, and D, our reactants A and B, with their stoichiometric reactions represented by small letters, the A and B, C, and D. So we have there the products for C and D here. Using the law of mass action, we have the forward reaction rate for the rate constant forward times the concentration of A times the concentration of B. And also we have the formula backward reaction rate. We have here the backward rate constants times the concentration of C and the concentration of B, where the concentration of A, B, C, and D being the active masses, and the K sub F and K sub B are rate constants. Okay? So now let's move on. At equilibrium, forward and backward rates are equal, and the ratio of the rate constants is a constant. and is known as an equilibrium constant. In a reaction mixture at equilibrium, the concentration of the reactants and products are related by an equilibrium constant. So given again on the general reaction here, A plus B will give us a reversible reaction to C plus D. Then we have here, because it is directly proportional, then forward reaction rate is equal to backward reaction rate. Given the fact from our previous slide that forward reaction rate is equal to this one, and then the backward reaction rate is also equal to Kb times the concentration of C times the concentration of D. As this goes, we are going to get the final formula for the coefficient of the equilibrium constant rather. So we're going to put divide concentration of A and B from both sides times the backward concentration rate, constant rate rather. So what we're going to do, cancels all the same stats, like AB here cancels out, and then the KB divided by KB, so cancels out. That will leaves us to forward over backward is equal to the concentration of C times concentration of D divided by concentration of A times concentration of B. We also know that the equilibrium constant is equal to the forward over the backward constant rates. Therefore, given this equation, we are going to substitute on this data. So, what leaves us with the formula, the equilibrium constant is equal to concentration of C times concentration of D all over concentration of A divided by concentration of B. Now take note that the concept of equilibrium forms the basis to understand concepts like ionization, hydrolysis, acids, bases, salts, and buffer solutions. This applies to all, as long as there is chemical reactions in every chemical solutions. For example, here we're going to compute the equilibrium constant of the solution. Given we have the nitrile chloride is in equilibrium with nitrogen dioxide and chlorine gas. So they are formed. What type of chemical equilibrium is this? Very good. That is a homogeneous chemical equilibrium. So, given the concentrations in moles per liter, we have here the nitrile chloride and also the nitrogen dioxide and then the chlorine gas. Here are the molar concentrations. So we have here our solutions. We have the formula. Chemical equilibrium constant is equal to the reactant, the product over the reactant. So raised to the power of 2 because there is a coefficient of 2 in NO2 to balance the general equation. And the same manner here, there are 2 moles of nitrile chloride. So let's just substitute the values of the molar concentration of each products and reactants, and that gives us 0.558. Remember that the constant equilibrium, the equilibrium constant rather, is unitless no matter what happens on on our formula. It is always unitless. Okay, so how about discussing Le Chatelier's principle? Why is it important in chemical equilibrium? This explains why. This Le Chatelier's principle, a system at equilibrium reacts to a change in variable or by stress by minimizing that change. If a change of condition or stress is applied to a system at equilibrium, the system responds in a way either by shifting its equilibrium position to the right or to the left. That best tends to reduce the stress in reaching a new state of equilibrium. So there will be another change of equilibrium state for chemical reaction the moment that there is any change in the system. Now let's discuss the factors affecting chemical equilibrium by stress. So there is change in concentration. Either a reactant or product is added or removed. Therefore, there's no change in equilibrium constant. That's what I'm saying earlier. We have the Kc or the Keq. Now the second one is change in pressure and volume for gaseous system and equilibrium. Therefore, there's no change in the equilibrium. All we have to do is to recall the Boyle's law, which states that in every increase in pressure as volume is reduced and decrease in pressure as volume is increased. Now the third factors that affect chemical equilibrium is change in temperature, but changing the temperature means changing the value of the equilibrium also. Remember that on the hydrogen and iodine producing hydrogen iodide, there is an application of temperature over there. So that applies to the factors affecting chemical equilibrium by stress. Take note also that introduction of a catalyst to a system at equilibrium changes the rate of the reaction but cannot shift the equilibrium in favor of products or reactants, because a catalyst affects the activation energy or the EA of both forward and reverse reactions equally. It changes both the rates equally. Equilibrium is established more quickly in the presence of catalysts. And a little fun fact, Fritz Haber was a German physical chemist who was awarded the 1918 Nobel Prize in Chemistry for developing a method of synthesizing ammonia from nitrogen in the air. He is also recognized for his supervision of the German poison gas program during the First World War, being known as the father of warfare. So, before we end our class today, I would like to check whether we achieved our objective for today or not. So first, can someone explain to me what is meant by chemical equilibrium? Wonderful. Thank you so much for your response. How about write the equilibrium constant expression for any reaction? Wonderful. Thank you for volunteering yourself. Now, how about applying the equilibrium constant to reflect changes in the chemical equation? Great. Wonderful. How about calculate an equilibrium constant from concentration measurement? This is so easy that we have discussed earlier on the formula. Nice. Very good. Good job. How about lastly, explain how important Le Chatelier's principle in chemical equilibrium? Wonderful. That's too easy to answer. Great. Since we have all achieved all our objective for today's lesson on chemical equilibrium, I would like to say thank you for your presence for today, and have a great day. Goodbye.